Zar Desai here for you. He's going to talk about OpenCanary. It's really exciting. It only was released a month ago, I think you said.
Yeah, just over a month ago.
So it's going to be very cool. So kick us off.
Thanks, Devon. So, I know the last talk mentioned security, but when the slides come up, we'll have another talk about, we'll turn our attention to security, but of the computer variety. Let's just find out where the slide has gone. So now that we're done fiddling with the various dual monitor setup, let's turn our attention to a security problem. So as an introduction, I work at a applied computer security firm called Thinkst. We really enjoy our computer security, and we like to aim at problems that others tend to avoid. So although we're a small company based out of South Africa, the code we write is deployed at several companies that many of us use every day. And I must mention, though, that the work in this talk is not done by me alone. There's a team of us, and the others are vastly more impressive than myself. They've been doing talks, writing papers, giving trainings across the world in this area long before I ever wrote my first Hello World in Python. So the plan for today is I just want to give a brief overview of the way people use Python in the computer security community. It's not very different to the way anyone else uses it, but just in case there's a few niche stuff that people may not be aware of. And then we'll talk about the actual subject of the talk, which is honeypots, the thinking that led us there to this thing, and then onto OpenCanary. And then finally what I'd like to do is just finish off with some interesting sort of day-to-day problems that we hit our heads up again during the working and stuff. And the main reason I want to do that, I just want to show how Python plays a big role in that. Just because we're at PyCon and there's very few places where you can get up and, sort of sing an ode to Python. May as well make it this one. So in the security community, Python is almost the de facto language, the go-to language that people use. I mean, it's used all over precisely because it has such a great standard library to write libraries, tools, frameworks, and of course very usefully as a plugging language. Some of the more useful things is, so for example, in the debugger IDA and GDB even, it's easily extensible using Python, and it's indispensable for reverse engineers and exploit developers. But one really cool framework that I don't think many people may have heard of, has anyone heard of Innuendo? Okay, so Innuendo is really cool. It's a framework for writing implants for malware developed by a company called ImmunitySec. And the really interesting thing about it is you can write your implant in malware and extend it using Python. It's quite remarkable, just given the fact that their malware is very sort of flexible, and it can do things like execute within a completely legitimate process. I just thought it was it's a very nice example of Python well used. At Thinkst, so we like Python for many of the same reasons that you do, and we have several active projects going on it. But the one reason that I've really come to appreciate about using Python is just that it's really for those really times, those really pressing times where you quickly need to experiment and test that idea to see if something works out. That's something I really appreciate Python for, and towards the end I'll show how that works out. But for now, let's turn our attention towards honeypots. So honeypots are clearly a very old idea, and if the published record is anything to go by, the time for this idea has certainly passed. I mean, it's quite outdated, and people don't really give it much serious thought in most quarters. But back in the heyday, in the early 1990s, there were a few papers that sort of catapulted honeypots into sort of general attention, and that sparked interest in them. There's one paper that I have to mention, just from 1991 at AT&T Labs. The guy called Bill Cheswick wrote a paper called An Evening with Burford. It's called An Evening in Which a Cracker is Lured, Endured, and Studied. It's a bit of a silly title, but I assume it would have been appropriate for the early 90s. But what he did was he just described his approach to setting up a sort of fake fundable mail server in order to watch some random person on the internet attempt to exploit his mail server and sort of try to gain further access to more computers, but all within a jailed honeypot. But there's one observation he makes during this paper that has aged very well over the past decade. He just says, A, setting up this honeypot took a lot of work, and B, he wasn't really sure whether it was worth it, because he wasn't really sure whether they got much out of it. So over the next decade, the honeypot research continued in that line. And so by the early 2000s, the HoneyNet project is established. I think some of you will have heard of the HoneyNet project, especially some of those security guys in the back. And one of the key aims of the HoneyNet project was to say, okay, we're developing honeypots and we're using these to study attacker techniques, tools, and their motives as well, and then sharing that with people. So far, by the early 2000s, things are going well for honeypots, and it stars on the rise. But then this is where things start to go down. And I really like this diagram because it really is such a great summary of the history of honeypots to date. So this is the summary of activity on the HoneyNet, on one of the major honeypot mailing list. And it definitely peaks early 2000, and then there's a long decline to nothing today. So it's in this long tail of decline that I just want to quickly turn to and speculate as to why did they stumble. I mean, these HoneyNet guys and everyone else was quite enthusiastic about what they could learn from them. So I don't want to go into too much detail about this. If you're more interested, we can chat later afterwards. But the one reason I do want to focus on is that I'd argue quite strongly that honeypots were pitched with the completely wrong criteria. So remember, I mentioned the HoneyNet project emphasized that they wanted to study attack techniques. So, I mean, it is an interesting use at the time. We didn't know that much in the early 90s. But it's still a limited way to think of honeypots. But further on, honeypots started earning quite a bad reputation as not living up to this ability. And we think there's something missing. So even if the honeypots fall by the wayside, there's still a problem that remains unaddressed, right? Even if we don't have honeypots on a network, we still really want to know when something bad happens on a network. And it's clearly a problem that we're really bad at today. So nowadays, in order to keep up with security news, I realize that I no longer have to follow specialist news sites. I can just read the New York Times and follow the headlines, and then I'll have heard about the Target breach, where they stole a whole lot of credit card details, the OPM breach in one of the US government departments, the NSA's breach of Belgacom, the Belgian Telecom, and of course, everyone's favorite, the Ashley Madison breach. The one thing that these breaches have in common is that there's a lengthy period, sometimes often as long as a few months, where we have other people that shouldn't be there lurking on someone's internal network and seeing what they can find, scraping up as much data as possible, and then exfiltrating it back home or wherever else they want to take it to. So it's a healthy assumption in general that somewhere on a large network, it's inevitable that a breach will occur. But what this honeypot history was suggesting to us, or in combination with this problem that we are thinking of, is why does that internal lurking have to go unnoticed? Because surely there's a long window period of activity happening, and there's a lot of things going on. So this is where we think honeypots can be refocused to tackle. And this is precisely the use case we want to focus on. So I refer to this as the canary use case. Canary as in canary in the coal mine. And what we like to do is use honeypots to flag when something definitively bad happens on a network. So something that we know is a very strong signal of something going wrong. And this is in contrast to sensors or sensors of many sort, which report normal and bad traffic, and then attempt to distinguish between the two, or try and figure out what malicious traffic looks like, or continually learn and update what they look like. So, for short, I'll often refer to this type of honeypot just as canary, interchangeably in the rest of the talk. But before I leave this general topic of the actual use case of honeypots as a canary, I just want to mention that honeypots are not the only ways you can do this, right? This is also an old idea of using something that gives you an indication where something incontrovertibly bad has happened. So some companies embed fake canary credit card numbers in their real credit card databases, so that if they see the fake credit card number pop up on the internet or on a carding forum somewhere, then they'll know something has gone wrong. Someone has seen that database. But I mean, you can also imagine extending that idea to, say, Word documents or PDF documents. Imagine exploring the way we can detect if a document has been stolen and it's suddenly now been opened somewhere on a computer connected to the internet. So incidentally, we have another project that explores that area that's called Canary Tokens. But for today in this talk, we'll just want to focus on the honeypot use case. So the honeypot that we've been developing is one called OpenCanary. So we just released it last month at a security conference called Black Hat. and it's a BSD licensed honeypot focused on exactly this use case, alerting on incontrovertibly bad action. So just to give you a rough overview, you have several OpenCanary daemons running, and these daemons all have a particular sort of fake protocols emulated, and if they trip, then they'll send an alert, and those alerts are sent to a central correlator, and you'll get an alert. So the honeypot daemons are mostly twisted based, and it's almost pure Python. I say almost pure Python with a little bit of regret, because Python was really great and it got us very far very quickly. So twisted, for example, is a major boon in getting a lot of this stuff up quickly. But there's some problems where there just weren't the tools to help us, and we didn't want to go that route. So for example, one of the things we needed was a full Samba implementation, so we could have Canary honeypot join Active Directory domains, which is what you'd expect in a typical corporate network. And there wasn't a Python option. And I'll mention later on that there's a commercial version that we work with, and in that we needed to mangle IP packets. And for that, we erred away from Python and went instead with a kernel module. So as an overview, roughly that is what it looked like. So you'll have some sort of network. Canaries will be scattered throughout an internal network. They'll report these events to a correlator. And the important thing is that every single event that a single canary reports is meant to be one that an action should be taken on. There's definitely something going wrong. So in case one of your canary daemons runs an SSH server, if there's a login on the SSH server, then that generates alert, and we hope you'd pay attention to that. So if there's a brute force of that SSH server, then the correlator will just roll up the events into one alert. But importantly, there's one important distinction to make here, which is not often seen in other more traditional honeypots, is that this is not intended to be run on an internet-facing computer, because I think you all know when you just put a server out there on the internet, there's just going to be people SSH brute forcing, and it doesn't really mean much. But on an internal network, that's a much stronger signal of something going wrong. And an even stronger signal is if you've prepared your honeypot to recognize public keys of maybe your important people within your organization. And someone's trying to use that key, then you're like, oh, maybe that key has been stolen and it's now been used on our asset. So I just want to give a really brief demo of a quick setup, and hopefully we'll be allowed to get back into that. But since we know, so which machine is this? Okay, so I've already set it up and installed in a virtual end. And I've already configured one. So what I'll just do is start an instance of it. The password is user if anyone's interested. It's just the daemons running in the background. So now let's just say on the other machine, someone's browsing on that particular network. So my speaker notes. Here we go. So I've color-coded in a cheesy way. So let's say someone has discovered that there's a computer canary out there, right? And then they decide, oh, well, let me just see what's running on that canary. So I've used the SV flag with nmap. That just means that it does the normal sort of port scan, check which port's open, but also goes a little bit further and probes the services to figure out what versions of services are running. So in this case, the OpenCanary is running Samba and MySQL, and for example, within the OpenCanary config, you can modify that exactly what shows up in that Ubuntu thing. I was arguing that I was considering showing a random message in there, but I was advised that it's unclear to mess with it, rather just show a default banner so that it's clearer. But the important thing that happens is the alert will get sent, and unfortunately my phone has been on silent. But it'll come through. So I'll just leave that running. The alert should come through. If it doesn't, then I'll have a little bit of network troubles. But let's carry on from there. So within OpenCanary, there's not just Samba and MySQL. We've implemented a whole slew of protocols, and the aim of emulating these protocols is that we want to alert early on in the protocol, and as early as possible, so that we know that something has gone wrong. So often we don't have to emulate the full protocol. So our motivation in choosing some of the modules is that we try to choose modules that will get in the way of a typical attacker. So some of the people on our team have been doing pen testing for many, many years, and they have these sort of favored habits that they go to as easy as when they're breaking into a network, just to do what they need to do. And what we like to do is aim some of these services to be in a way that if someone is in a network, they'll need to look at stuff. So like one thing people don't often think about is an HTTP proxy. So sometimes when you've first breached a network, you're sitting on the box, and now you need internet access from that box, but your computer can't directly link out. It needs to go via a proxy, which is not very uncommon in a corporate setup. So you could just do a quick port scan for a whole lot of HTTP proxies, try and find an open one, and then use that. So if there's if a Canary daemon's running an HTTP proxy, they'll hit that, and then when they try login, an alert will be sent. So you'll know there'll be something to look at. But at this point, adding modules is quite straightforward. So I just want to take a look, for example, at the SIP module. So it's slightly more of an unusual case, but we just thought that if someone's issuing SIP requests across the network, it's definitely something going wrong. So it's really quick and short piece of code. That's the whole thing. And in part, it's due to Twisted handling a lot of it. And then OpenCanary handles the alerts that happens at that log method. But some of the criticisms that we get when we propose the idea of using honeypots is that, for one, the criticism that people often bring up is that, okay, well, surely we can fingerprint the honeypot. So I don't want to get into too much details, but for the fingerprinting question, the one thing we are trying to do is turn the tables a bit. Often people refer to the attacker having a better game in that the defender has to make one mistake, the attacker has to win once, get a breach, and things work out in their favor. What we'd like to do here is turn the tables in some sense. So here, if you have a whole lot of demons scattered out, the person lurking around your network has to make one mistake in order to set off an alert, or one mistake in not properly fingerprinting it correctly, before actually deciding, great, ignore that, that's going to trigger an alert. And the second thing we do is we can also fingerprint on alerts. A lot of fingerprinting is actually very, very distinctive, so I'll mention a case of that a bit later. The one thing that's I think will probably cross most of your minds of people who work in open source software is, okay, well, look, a lot of these other honeypots have frozen into disuse. So many of these honeypot projects are unfortunately no longer left standing. So for OpenCanary, we actually have quite a nice arrangement in that we have a commercial version running alongside, so the two projects can support each other. And it's been mutually beneficial in both ways. In one way, we have fixes we're doing from one get put into other, and thanks to some cool contributions from the community, we've been actually learning some nice stuff from what other people want to do with it. So Things Canary is just effectively OpenCanary pre-installed on a little box with a very easy UI for setting it up, and you can manage a whole host of them on a web console. So just to give you some idea of where we've gone with this Canary subject in general, of the deployments that we've done with Canary, we've managed to spread a fair way across the globe so far. So I only mention this in part because for us it was an initial validation of the idea, the fact that we could deploy the same idea and have it working for companies or organizations from Silicon Valley all the way into the Middle East. So for us that was quite a validation of the idea. But the main reason I mentioned this is just to say, as always, with a little Python and a little elbow grease, we can really push tech out there. And thanks, by the way, we're a big fan of locally produced tech being used worldwide, tested out there. It's, really like seeing that happening. We know some of you guys doing some really cool stuff, and it's generally quite pleasing. So in the beginning of the talk, I mentioned I just want to chat about how Python helped us get to where we are. So to do that, I want to take you on a little day-to-day tour of some of the little problem-solving things that we ran into while building this stuff. So I'll just touch on 3 recent episodes where Python was pretty useful. So I mentioned earlier that we were marking up a whole lot of protocols, and one of the ones we wanted to do was Microsoft SQL Server. When you're emulating, it's things people want to see on a network. And the part we're most interested about implement about this protocol is just the authentication, the login. Because someone's trying to log into your database, and it's a completely fake database that no one should be using anyway. Clearly something's gone wrong. Normally, I'd approach a problem like this by setting up a default MySQL server, setting up a client, and then watch the traffic on the wire. And then for good measure, I also consulted the documentation. So this is what MSDN told me I was going to see on the wire. But that didn't quite happen the way the docs promised me. What actually happened was the initial setup message goes through, I'm in my SQL client, and there was a little flag that said something, something, encryption, something, something. I can't remember the exact phrase, but that had something to do with encryption, and I wasn't really sure how the flag was being used, but there was a flag and it was set. And then the server sends another, the same, or well, its own init message back, also that same flag. But I mean, up to now, the protocol's fine. I mean, we can easily fake this message. We know exactly what it looks like. But the problem here is we couldn't see the rest of the protocol because the connection was automatically upgraded, opportunistically upgraded to an encrypted one. So we had several options at this point. One would have involved poring over the MSDN documentation and trying to get a much more deeper understanding of the protocol. But we're looking for a quicker way to figure out just the authentication part. And this where Python, like the superhero it is, came to the rescue, in fact, with Twisted. So it turns out it just took about 10 minutes later, and we had a TCP proxy written in Python, and all it did was pass the traffic through and look for this particular byte string and flip that single bit from the client, fit the single bit back on the server, and everything else continues on pass, and we could see the rest of the protocol and continue to mark it up. Just to give you a sense of how easy it was, that's the one half of the protocol. Literally copy the data over, and if you see this thing we're looking for, just flip a bit in it. So it may sound a little bit more straightforward now because I told you in the beginning that bit was the encryption bit and that's how it was using. But before we set off in the problem, we weren't really sure how the bit was being used. And the great thing about being able to quickly mock it up was that if we were wrong, then we wouldn't have wasted that much time. We could quickly go back and try another route. One of the other things we wanted to do this time in the commercial Canary version was spooling Nmap. So I know we've mentioned Nmap already, but for those of you who are not aware, Nmap is this all-star sports scanner. It's the heavyweight sports scanner, but it also does a lot of other things. One of the other things it does is it can fingerprint an OS based on the peculiarities in the network IP stack, right? So amidst many TCP, IP, UDP standards, there's always little bits of corners where implementers can do things slightly differently. And those are the sort of quirks that Nmap tries to pick up on to be able to distinguish which OS is running on a host. So how Nmap's OS detection works is it sends the exact same 16 packets to any host, gets those replies, and then runs roughly over 100 tests on those responses, and then it has a pre-compiled database of test results that it can match up with OS, and it just has an algorithm for matching the closest match. So knowing that at this point about the problem, we could go, oh, okay, well, the standard solution here is we write a kernel module or extend IP tables, and we'll start playing with that. But it's quite a bit more time-consuming to get to that point where you can quickly start playing. So again, here's another place where Python comes to rescue. But central to this approach is a module called NFQ that exists on Linux for IP tables. I'm not sure, has anyone used NFQ? Ah, great. Okay, so you guys are all pretty much familiar with it. But for those who aren't aware with it, it essentially just allows you to set up a rule where you tell the kernel, okay, this packet is coming in. Now, instead of using a rule in IP tables to determine where the packet must go to, you say, okay, well, IP tables pass this packet to user space, and a program there will pick it up and will decide what to do with the packet, and then we'll tell you, and then you can carry on with the rest of your work. And it can even modify the packet, so that's often quite useful. The nifty thing about this is that, of course, the user space, if it's just a user space program, it can be written in Python. So as a really nice thing, a very easy thing to do is if you just want to quickly pick up those packets that I just sent through with this particular IP type tables rule, if you want to pick it up in Python, you can literally do it in, I don't know how many lines that is, but that looks like very, very little very little lines. So what this code is just doing is saying, okay, well, if I get a ping packet, so this ICMP echo request is just saying, okay, well, just drop that packet, and everything else passes through fine. But since we're playing with Nmap here, right, we don't just want to figure out which packets Nmap is sending to us, because now we know how we can test all the various features of Nmap packet. We also need to send a reply. But I don't know if you noticed in the previous in this slide, we're using Scapy, which is also a wonderful packet manipulation tool that a lot of security people use. It's just their go-to thing when they need to flip bits in packets. And again, a very quick little addition, and we're sending ICMP packet replies back. And the cool thing is that we can just change anything we want about the packet, including the payload, all sorts of random details one would never, one's often not interested in. So in the end, we didn't actually go with this method, but it was just useful for playing around, getting a sense of a problem. In the end, we actually had to go with the kernel module because it was a better fit with some other constraints we had. But the last problem that I want to mention that came up with the Canary is something called DNS tunneling. So one of the things you encounter on many big networks is that if you deploy a device and you try to connect out to whatever server you set up, and you say, okay, you asked the Canary to connect to, I don't know, initially we thought we could just open a TCP connection out to the internet and then maybe send syslog messages or something to our log server. But we quickly realized that so many networks by default are not going to allow you to randomly do that, and the administrative hassle of getting someone to open a port for you in a very large organization can be incredibly time-consuming and painful. But all hope is not lost. So often in a lot of these network setups, it's still possible to use DNS, right? I mean, you can't, I assume some of you are familiar with the subject, but I mean, you can't make a direct connection out, but you can do a DNS query, and you do the query, and then at some point, so in this case, our Things name server will know, okay, someone somewhere looked up. I'm covering out a little bit of details, we'll come to that, but somewhere, someone looked up this particular query, and we know they looked at that query. So we can really extend this idea a bit and say, okay, well, why don't we set up our own special domain with our own special name server, and we ask the Canary to do a query like this, host.myfirstmessage.canary.tools. So now, when our name server, specially set up, gets this query, it's like, oh, okay, someone tried to look up an address, and the subdomain they sent to was my first message, and now the server knows the message. So now we have a way to get information out of a network to our correlator. Does anyone have any ideas, by the way, or a guess of how we can get information back in? Someone's nodding. What are you going to say? TXT, exactly. Okay. So for those who are not familiar, instead of actually let me do the build-up since you guys have beaten me to the actual solution itself. So I mean, you could try something like encoding your message in an IP address, and if that's too small, maybe you could switch to IPv6 and then you have a little bit more space. But that's still quite painful. Luckily, there's other types of records called TXT records, and what it is you look up the record, you get back a text description. So now we have information going in and out. So to tie that together, how the Canary can now communicate out of this network is it can do a text record lookup, and the message will be encoded in the subdomain, and data will come back in the value as the text record. But so I mentioned earlier that I was glossing over a whole lot of details. And the most important detail that I'm glossing over is the fact that DNS is connectionless and quite unreliable. So there are a few problems to solve. So I just want to quickly, I know the slide's a little bit heavy, but I'll just quickly run through that just to give you a sense of what it takes to finish the problem off to get it into a production state where it works out there in the real world. So firstly, people won't be very happy if you're sending network originating from their data originating from their network out in the clear text onto the whole internet. You'd probably get kicked out of on first suggesting it. So the simple solution is do some sort of encryption. So we use NACL. And then the next problem you run into, of course, is that you can only use a certain amount of characters, a certain type of characters in the DNS query. So case-insensitive letters and numbers and a hyphen. So you'll need to do some sort of encoding. we used base 32 encoding with a slight modification. But I mean, you can always invent your own custom encoding that's a lot more efficient if you need to. The other problem that also comes up is that because of DNS caching, if your canary does the same request twice, somewhere along the line in the chain of DNS servers that are queried to look up this answer, somewhere one in the middle is going to say, oh, I've seen this query before. We don't need to go check the actual name server. Yeah, I'll just send you the old copy. So we get around this in two ways. The main thing is just, hey, you append random data. So there's a very, very, very slim chance you'll ever send the same DNS query again, even if you're sending the exact same message. So you just use some random padding. And another thing that just to be on the safe side, to lower the probability of it ever happening, you could also just lower the TTL on the DNS record so that they won't cache it for very long. And the other more simple problems is limited size of the domain range. You can just chunk your message into several queries. And for repeated queries, that sometimes happens. So you just need to add packet IDs so that your thing receiving the queries knows, okay, I've seen this packet before. We can safely ignore it. So if all of this day-to-day stuff sounds fun, this is the kind of fun we had working on this. So if this sounds interesting, you're welcome to come joining and play with it. OpenCanary is BSD licensed, so you can do pretty much whatever you want to do with it, and test deployment on live networks. We'd love for you to try it out, send code and criticisms. I've been learning a lot from some of the code contributions that have come in, so that's been pretty cool. So some parting thoughts. If you're keen, do jump in. If you want to explore those other canary options that I mentioned that are not honeypots, but other things that alert on incontrovertibly bad actions, you can take a look at our other project called Canary Tokens. And the last point I want to mention is that I just talked about one very, very, very specific security problem here, but there is lots of great room open to build and break better security. People are doing a lot more exciting things than those old school antiviruses and firewalls and really boring stuff. And since you're in this audience, you're very well equipped to be tackling those. So look out for contributions you can make. I'm sure you'll have cool stuff to do. And that brings me to the end. Thanks, guys.
This is just a thought. You said you were appending random data so you didn't have the same query twice in a row. Instead of random data, why not append a timestamp? Then because random data can be the same twice in a row, a timestamp is guaranteed not to.
That's actually a good idea. Yeah, that's not a bad idea. That's quite a good suggestion. Thanks.
So I did see you mentioned Kippo there,
Yep.
and I'm guessing that you've probably dealt with the Kippo upgrade problem at some point.
Yeah.
You kind of glossed over your own, but what about an upgrade thing there?
Oh, yeah,
So
yeah.
How are you guys planning on dealing with that?
Because our solution it's really quite a small problem. The thing's pip installable, so you just pip install, use your usual pip
But your
process upgrade.
database of things, do you keep anything local, like the Kippo artifact store, or anything like that? How do you deal with that kind of thing?
On the Canary daemon side, it's just the daemon and a config file. You can update the config file as you want. The correlator is separate, but we're not so sure whether people in the community want to use that correlator or not. If they do, that's great. But you can also hook the daemon up to whatever other device you're using. So someone last week just pushed through some code for hooking it up to this other honeypot infrastructure called HP feeds. I think that's the name. So you don't even have to use that. In that case, you'll just have one daemon, and your only state will be the config file. So that's all they used to update.
And then just one last question. On the DNS, I see you've got no forward error correction or anything else on responses. So if you want to, chunk a message over multiple requests,
Yeah.
or on the response side, the receiving side, a retry mechanism, anything.
Oh yeah.
Do you have a low enough message
yeah.
volume that you don't need
Yeah.
that?
So we definitely have a retry mechanism, especially since sometimes if you're going to have a brute force. So far we've been handling brute force actually surprisingly quite nicely. So we've had someone, against our good advice, had deployed one of these devices on the public internet, and it was getting hit with an SSH, typical sort of SSH brute force, and was holding up quite well. What happens then is we have a retry queue, so it does get holded at all.
But nothing in China and Russia either. Intentional or accidental?
So To be honest, there's a few devices that I'm not actually sure where they are. I know they're reporting in, so there could be some in the region, but no, we haven't done that. It's not intentional, no. If you're from that area and would like to try it out, be my guest.
I just comment, there is one honeypot project that still works, but on a very limited scale. It looks for email spammers and actually gets the law involved, and that's a sister company of Cloudflare called Project Honeypot. So that's one that's still working.
Oh, cool. Yeah, no. There are definitely some
Yeah,
still
yeah,
working.
yeah,
I don't mean
yeah,
to
yeah.
disparage the whole thing.
Yeah.
I just
but,
mean to say that
but
we're
that's
taking a slightly
very
different
limited. It's
direction.
just looking for email spammers. But yeah, that looks like an interesting tool you've got there.
Any other questions? Oh, there we go. You're hidden.
Yeah, I was just wondering what sort of information you're transmitting over that DNS interface, because a lot of companies might not be happy with you having this kind of black box inside their network that you can then communicate with.
Sure, but I mean, so you mentioned this problem, right? But a lot of companies will run something like those third-party mail server scanners. So, I just want to mention a brief anecdote, just to give the interest. Some people are actually surprisingly comfortable with the idea. And in this case, we're only sending, we're sending data that could be suspicious. Though you're saying that we could be sending more data about the network out than is absolutely necessary. Yeah. So, for one, they can check out the OpenCanary source code, but they probably are also running other things that can send data out the network. So, companies that run third-party email scanners. If you've ever embedded those, if you ever run phishing campaigns and you've embedded links in those emails, you can often run, if you run a phishing campaign against a company that runs a typical third-party mail server, you'll quickly find that there'll be a whole lot of hits before someone has even seen the mail. So you'll see hits all over the world. I remember looking at one case when we were doing for a service we run. I was trying to debug why this client had so many hits on a particular email campaign when they just sent one email campaign and it wasn't open. And like the hits were bizarre. It was hits in several places in the Middle East, in Germany, in Moscow. I was like, I can't possibly imagine a person being in all these places and reading their email. So it turns out the answer in that case was their third-party mail scanner, and potentially it was passing on to their partners for analysis. But yeah, there's some measure of trust that has to take place, but they can view the code.
Just to follow up on that, what are you actually sending in and out?
Oh, okay. So that's a good question. So we only send, the typical example is we send information about that particular event. So we'd send, so if it's an SSH login, it'll be the public key of the login, username, password, source IP address, source port, destination port, time, the type of event, and that sort of thing. I think I'm pretty much covered, pretty much covered the meat of it. There's not stuff like listen on your Intel network and send everything else. No, it's just the actual events.
Hi. I was just wondering
if
you had any techniques that you use to try and make these hosts seem really attractive to attack.
Just to make the honeypot seem really attractive.
Yeah.
So the one thing that we do is, the one thing we do is when we join an Active Directory domain, someone is enumerating all the machines. That could be a way to be discovered. So we are actively exploring more ways to make them discoverable. For the moment, that's the most interesting one we have. The rest will rely on someone just doing a typical network-wide port scan and picking up the service the way they usually would, which is a bit noisy. But you're right, we definitely need to work on ways of making them more discoverable.
You said in your plugins or modules, as you call them, that you try to catch it as early in the sequence as possible. So I was interested by SIP, but it seems like you've got a very, very basic SIP handler there,
Yeah.
actually.
So it is quite a basic handler. So for the SIP one, we're just saying, in this case, any SIP requests to this blatantly false unused device should be
Okay.
treated with suspicion.
So something like TFTP, where you might sometimes have a writable TFTP server or like a web dev that you can upload to, those kind of
So-
things. Do you emulate to that extent?
So with the TFT thing, again, with the TFT, we consider it in a similar class as the SIP, in just that any activity on that is not considered useful. But one point I should mention that's very different is something like Samba, for example. We don't consider browsing the file share to be an event, because I'm sure
Yeah,
you've
you've
seen
got to
many cases
discover
where
it
you
attempts,
accidentally
yeah.
discover the thing. So in that case, we consider pulling files to be an event, which is
Okay, so
stronger.
you've got a kind of a degree of scope on which
Yeah.
you will evaluate. Okay.
If you have ideas on ones that should be changed, if you think some alerts aren't strong enough, I'd be interested to hear. Thanks.
Well, thank you, Azad. It was very, very interesting.